Hi folks, welcome back to Physics with Captain Rod. The purpose of the video is to give an example here of drawing what are called shear moment diagrams for a beam under various load distributions. So what we're looking at here is we have this beam that we can see in this picture. It's got this 50 pound per foot distributed load over this first 20 feet, and then in addition to that, it's got a 200 foot-pound couple moment applied clockwise at the end. Now, for the purposes of shortening the video up, I've went ahead and already found the reactions that I called AY and BY acting on the beam and put them in the picture. So if you're not sure how those were found, again, go back and look at some of my previous videos about finding reactions. But basically, I replaced the 50 pound per foot times 20 feet here with a single 1,000-pound force acting 10 feet over, and then wrote a couple of moment equations to get AY and BY. So what I'm going to do is just pick up on it here. So again, the idea is we want to be able to determine the shear force internal within the structure everywhere from A all the way to C, all right, and the internal bending moment. And the way we do that here is we're going to start with a cut here. So I'm going to imagine cutting this beam maybe about here at some location. Let's just call that X. And then what I'm going to do is draw a free body of the beam. Now I'm putting a coordinate system inherently on the left-hand side of this, so plus X is going to be to the right. So I'm going to go ahead and make my cut now. And the nice thing is about this program here is it works really well for this. When you're working these homework-wise, you typically must just recopy it, but I'm going to go ahead and make my cut. And again, that's at kind of an arbitrary value of X. Okay, and I'm going to just do my free bodies over here to the right. Now, clean this up a little bit. Let's get rid of these arrows here. Now, what we're going to do is first let's talk about the distributed load. So we got this 50 pound per foot, but again, remember I'm cutting it right about there in my picture. So this part of the distributed load belongs in this free body and nothing else. And remember, when you're dealing with a distributed load, this area here gives the force vector, and it's going to be at the centroid of this geometry here. Now this is a rectangle. This dimension is X. So what I'm going to do is I'm going to replace this distributed load with a single force vector down. The magnitude of that force is going to be 50x, and I'm going to put NCU for note consistent units. That's coming from 50 pound per foot times X, and then it's going to be at a location of X over 2, because if from here to here is X, the centroid of this would be right in the middle. So this is going to be X over 2 from here to here, and another X over 2 from here to here. Now, in addition, we're going to have the force AY, 490 pounds acting up. I'm just going to call that a 490. Now, at our cut here, we're going to have an internal shear and bending moment. Now, glancing the free body over, there are no horizontal forces anywhere, so there's no reason to put a normal force here. You know, if we thought it would be there, we'd put that normal in this direction. But again, looking at the free body, there just is no reason there would be an internal normal force here. Now, these are again in their assumed positive directions. Had we did a free body of the right-hand side of this cut, this shear force would be up, and this moment would be clockwise, because you have to be consistent with Newton's third law. All right, so now we just start writing equations here. Equation number 1, I'll start right over here. Sum of all forces y direction equals 0. I'm going to go ahead and do up positive. So that's going to be 490 minus 50x minus the shear, and that's it, equals 0. So our shear force is going to equal 490 minus 50x. And again, you notice we got a linear function here, which is perfectly fine. Next, sum of all moments has to equal 0, counterclockwise positive. I'm going to go ahead and do the left end, put a little L here for left end. If we're summing moments about the left end or about point A, this 490 doesn't produce any moment about A. This force does, however. We're going to have the magnitude 50x times the moment arm x over 2, and that moment is going to be negative because I'm doing counterclockwise positive, and this force produces a clockwise moment about point A. Next, the shear force. That also is going to produce negative moment because this is producing clockwise moment about A. The magnitude of that force is 490 minus 50x. And then the moment arm is the distance from here to here, which is x. So again, this is the shear force times distance. And then we have this plus m here for the internal bending moment. So again, that's the bending moment applied basically right there. And that's it, equals 0. So our internal moment is going to equal, let's see, being kind of careful here. Let's talk linear terms first. Here's a linear term, minus 490x. If you add that to the right, we're going to have plus 490x. Let's see. Here is a minus 25x squared. I'm going to go ahead and just add that to the right and call that plus 25x squared. And then here is a plus 50x squared. And we'd have to subtract that to both sides. So that's going to be minus 50x squared when we put that over on the right. So what we end up with here is that the internal moment here is going to equal 490x minus 50x squared. So here are functions here and here that are good from x equals 0 to x equals 20. Now the reason they're good all along here, there's no real changes in load here. If we had maybe a single force vector here acting in addition to that, we would have to do a new cut. You have to do a new cut every time there's a change in load. So our first cut is good anywhere from here to here. But at this point, this by represents a change in loading, so I'll be doing a new cut here in a few minutes. Now, as we move on, some things to check. Look at this left end here, and you'll notice that because of the way this is attached, there's no bending moment here. There's no possible way that there's a bending moment on the left-hand side. So I'm going to check my endpoint here. You'll notice if I put in x equals 0, we get 0 out of the bending moment, and that matches this condition, which is a good sign. Another thing I'm going to check here is this. The mathematical relationship between the shear and bending moment is this. The shear should always equal the derivative of your bending moment. And I'm going to check that to make sure I'm on track here. In this example, that's going to be 490 minus 100x. And I'm looking right here and going, that's a minus 50x. So this is indicating some sort of problem. So I'm going to, actually what I'm going to do here is I'm going to pause this because I don't want this video to get too long. I'm going to go back and reinvestigate this and see if I can determine what that problem was, and then I'll be back. Okay, and it didn't take me long to find it. But I look right here, okay, 25x squared minus 50x squared is minus 25x squared. So I'm going to go back, just erase this right here. Minus 25x squared. And then when you differentiate that, you now get minus 50x, which matches our shear function perfectly. Now, this had a little algebraic error, and I'm imagining that most people watching this video probably caught that right away. I'm going to leave that in the video because, again, I think that's a good example of how did I catch that. So as I'm writing these functions, you'll notice that I'm checking them against my initial conditions here. I checked that my internal moment was 0 at the endpoint, based on the fact that there's no moment here, no applied moment, and then I used that derivative to check my moment function against the shear function, and that's how I found that mistake. So I'm going to leave this as part of the video demonstrating, just how important it is to kind of keep track of your work as you're moving along. So I've checked it, it's good. I've got my two functions here. What I'm going to do now is I'm going to graph them. So here's my first function that I'm going to graph, and then here's my second function. And I think what I'm going to do here is just pause this while I sketch the graphs to keep the video from getting too long, because I've got a whole other part of this I have to do. So I'm going to do that and sketch these and come back. Okay, folks, I'm back here, so I want to chat a little bit about the work I've done and what we're looking at here. So I went ahead and graphed this shear function. Now I did so by the fact that this thing's linear, so I just put in 0 for x, got 490 out for y, put a dot on the graph. I went ahead and put 20 in for x, got negative 510 out for y. So this is the point here, 20 minus 510. went ahead and connected the dots. I went ahead and calculated the zero here because I knew I was probably going to need that later on here. This has a zero at about 9.8 feet. Okay, our moment function here, 490x minus 25x squared. So this thing's parabolic and it opens down because of this minus sign. I noticed that it went through the point 0, 0. I then calculated a value at x equals 20 and I got negative 200. So that's this point right here. I calculated the vertex of the parabola by looking for where the dm dx is equal to 0. I got 9.8. You can also just look at your shear function because the shear is the derivative of the moment. And then I ran 9.8 into this moment function, got 2401. So it looks like the maximum internal moment here is 2401 foot-pounds occurring at x equals 9.8. This zero here turned out to be negative 19.6. I got that by looking for the zeros of this function. One of them was 0, the other one's negative 19, or the other one was 19.6. So there's our graph of these functions. And again, these functions are good anywhere from 0 to 20. So what I'm going to do now is talk about from point B to C. So if you'll bear with me here. And I don't have room to keep all of this, so I'm going to get rid of this work. So if you're watching this and you need it for your notes or something, take a snapshot of it, or you can always go back and take another look. I'm going to clear that. All right, so now when we want the internal moments between B and C, what we need to do is we need a free body of this. Now, some people, what they like to do is go ahead and cut it and maybe do a free body of the other side. I don't like to do that. I like to just stick with one set of coordinates and move left to right doing my cuts. And I want to use this condition at the right-hand side to check my work. If I do a cut here and I look at a free body of this, I think it's quite possible that I'm going to use my condition on the right, or not possible, you are going to be using your condition on the right to derive your equations here, and therefore it's not really as valid to look at the endpoint to make sure that your moment function is good. So I'm going to go ahead and just continue on making my cuts left to right. That's how I tend to work these. Again, other books and other people like to do these different ways. I'm just doing what I usually do. So I'm going to go ahead and I'm going to do a cut somewhere in here now at an arbitrary distance x. Now in that picture, x is going to be from here all the way over. Some people like to even move their coordinate systems. I don't. I tend to just put a coordinate system in the problem and leave it for the entire problem. So I'm going to go ahead and do my cut. And again, at kind of an arbitrary x. All right. Now, I'm going to do a little work here. Whoops. For starters, I'm going to replace this distributed load. I'm going to get rid of it. And I'm going to replace it with a single force vector. At 10 feet. Now 10 feet is halfway between these rollers, so I'm going to come over here, put a single force vector down at 10 feet, and that force vector is going to equal the area here bound by the rectangle, which is 1,000 pounds. So we're going to have a 1,000-pound force at x equals 10 feet here. That's for the distributed load. We've got the force AY, don't need that anymore, up here on the end. And again, we know a value, 490 pounds. We have a force BY applied up here of 510. All right, so there's all my external loadings. And now again, we're doing this at an arbitrary x here. So in this example, x is from here to here. We're going to have the internal shear and bending moment applied at our endpoint here. So there's our new free body. I'm going to go ahead and write a force equation now. Sum of all forces y direction equals 0. Looking at our free body, and we're going to have plus AY. I'm going to go ahead and just put plus 490. And again, the units are consistent, so I'm not going to worry about it. Minus 1,000 pounds. Whoops, I said I'm not going to worry about it, so if I don't worry about it here, I should not worry about it there. Plus 510 pounds. for this guy, and then minus our shear force, and then equals 0. So our shear force, right, is going to be 1,000 pounds minus 490 minus 510, and we double check that, and we get 0 out of that. So interesting development, we might say. Now, one thing I want to take note of, you'll notice that, look at the end point here. There's no vertical force at the end point, so that shear force has to match that, and it does. Next, moment equation. Sum of all moments has to equal 0 about point A. Go counterclockwise positive, so summing moments about this point. We're going to have, let's see, minus 1,000 times 10. Right, so that's a 1,000-pound force times this 10-foot distance. Then we're going to have plus 510 pounds for this force times 20. Then we're going to have minus the shear force times x. Now I know that this is 0 anyway, but I went ahead and put it in just to take note, or just to show that I'm considering all forces. So that's this force times this distance. And then we got plus our internal bending moment for this guy, plus because that's counterclockwise, and then equals 0. So you'll notice here that it looks like we got a constant internal bending moment, and the value is going to equal, by the time we add this and subtract this, and what we get for our internal bending moment here is minus 200 foot-pounds, or pound-feet. All right, so you'll notice this one's not a function. Well, let's check some things here to see how we're doing. One, you'll notice that our shear force should be dm dx, and when we differentiate a constant, we get 0. So I look over here and I say, okay, that's looking good. Next was check our endpoint. Now, when we take a look at our endpoint here, so imagine a free body of just this little piece of it. You know, if I cut it like so, and again, this is just a picture of just the end. The end has this 200-pound or 200-pound-foot couple moment applied. Now, in this picture, I've got a, if you look at this cut right here, we have a counterclockwise internal bending moment. If I cut that and I do a free body of the right-hand side, by Newton's third law, that would be a clockwise bending moment on the right-hand side of this cut to be consistent, you know, by action-reaction. So that would look like this. So basically, this is the couple moment pair for this. They're in opposite directions because here this one is on the left-hand side of the cut, this one's on the right-hand side of the cut. There's no vertical loading of any kind here. And you'll notice here that this bending moment must be 200 foot-pounds opposite the direction shown. And that's why we've got a minus 200 foot-pounds here. So our internal moment is matching up the conditions at the end of the beam. And again, dm dx here is 0, so that's a pretty good looking sign. So I'm going to go ahead now and finish the graph here. So we found that the internal shear force was 0, so on this graph, kind of boring, but that is actually part of the graph. And we have a bending moment of minus 200 foot-pounds. So basically now this is constant. Again, this was minus 200 and not changing. So that's pretty well the end of the example here. This video is just about 20 minutes long. Some highlights here. To do internal shear and moment diagrams, you start with a free body of the entire structure, get the reactions. Then, for every load change you have, you do a cut and a free body. So here I did a cut, free body of the left-hand side. All right. Then at this point right here, the load changes again because of that BY and because of the fact that this load dropped off and it goes to 0 here. So I did a cut and another free body. Now, there are different ways to do this. Here's what I tend to do. I put a coordinate system on the left-hand side. I am consistent, and I just use that coordinate system throughout the entire problem. Then I tend to look at the conditions at the right hand side, and I make sure my shear and moment conditions, when I get these functions all the way on the right, they match the conditions on the right hand side. That's a good check to your work. And also check everywhere throughout the problem that dm dx is equal to your shear function. So anyway, that's 20 minutes 16 seconds. I think I'll just end this video right here. Some advice for you folks if you're working on homework: put your picture here and leave this space all free below your picture. It is very customary to put your shear moment diagrams right below the beam that you're working on, right? And even to scale, meaning that, you know, from here to here is 30, and in my graph from here to here is 30. Do your work off to the side. Make good, concise cuts, you know, like when I made a cut here and then a cut here, and draw very good, concise free bodies. Replace your distributed loads wherever appropriate with single force vectors. It's just important that you get them at the correct locations. You write force and moment equations to find the shear and moment functions. Check your shear and moment functions against your endpoint when you get done, and then sketch the graph. So hope this video helps with these things. Have a great day.